Hey everybody, in this video we are going to talk about the connection between work and kinetic energy. In physics, if a force is applied to an object and it moves, work is being done. What else is possibly happening? The object can experience a change in velocity, and if the velocity changes, the kinetic energy changes as well. This leads us to the work kinetic energy theorem. Under the work kinetic energy theorem, work is also the change in kinetic energy. It also states that the net work done by all of the forces acting on an object is equal to the change in the object's kinetic energies. The equation for the work kinetic energy theorem is net work equals to 1/2 mass times final velocity squared minus 1/2 times mass times initial velocity squared. Let's try out an example using the work kinetic energy theorem. On a frozen pond, Kira Sage kicks a 10.0 kilogram sled given an initial speed of 2.20 meters per second. How far does the sled move if the coefficient of kinetic friction between the sled and the ice is 0.1? Let's start with known information. The mass is 10.0 kilograms, initial velocity is 2.20 meters per second, and the coefficient of friction is 0.1. Lastly, the final velocity of this situation is going to be 0 meters per second. The reason for this is if we want to know how far something goes, therefore that would mean the object has to stop at some point. It also would help to draw a free body diagram of the situation. In this free body diagram, we still have the force of gravity, and we have the normal force as is the object or the sled sits on a pond of ice. And we have the delta x vector or displacement vector pointing to the right. And then if it's moving to the right, the friction force is going to be, in this case, pointing to the left. The only equation we have to solve for how far something travels is the work equation, which says the net work equals to the net force by the displacement times cosine of the angle. However, looking at this, we don't have the net work, we don't have the net force either, and the angle isn't explicitly stated as well. So we're going to have to solve for each one of those components. So let's start by using the work kinetic energy theorem to find the net work. Remember, the work kinetic energy theorem says work net equals 1/2 times mass times final velocity squared minus 1/2 times mass times initial velocity squared. And looking at this equation, we have all the values to solve for it. Let's go ahead and plug the values in. When we plug the values in, we get 1/2 times 10 kilograms times 0 squared minus 1/2 times 10 kilograms times 2.2 meters per second, and that is also raised to the second power. We can work that out, and by doing so, we'll get a net work of negative 24.2 joules. Next, we can go ahead and try to find the net force, and this isn't so bad because if we look at our free body diagram, you can immediately say that the normal force and the force of gravity cancel each other out. So with that being said, the net force has to equal to the force of friction. Going back, force of friction, since we're talking about force of friction kinetic equals to the coefficient of kinetic friction, mu k times the normal force. And in our problem here, the normal force is exactly equal to, or equal and opposite to, the force of gravity, mg. Looking at this, we have all the values. Let's go ahead and plug those in. Doing so, we're going to multiply 0.1 times 10 kilograms times 9.8. And then this will give us a force of friction, and also the net force of 9.8 newtons. The last part we're missing is the angle. And though it's not explicitly stated, we can kind of deduce it from our free body diagram. If you look at our free body diagram, the angle is, again, supposed to be the angle between the net force and the displacement vector. But we already identified the net force to be the force of friction, which is pointing to the left, and the displacement vector is pointing to the right. So based off of those two observations, we can say the angle between force of friction and delta x is going to be 180 degrees. Okay, so it looks like we have all the values necessary to solve for delta x, how far this sled goes. We have the net work, we have the net force, and then also we have the angle. So let's go ahead and plug the values into our net work equation. Doing so, we get negative 24.2 joules equals to 9.8 newtons times delta x times cosine of 180 degrees. This leads us to an answer of 2.46 meters, and then we can put the positive sign or the word forward to imply the direction. Alright, so that concludes our video on work, kinetic, and energy theorem. I hope you found it helpful, and thank you for watching.